Okay, let's get started. Probably this is the third class of talking about digital communications. So we are still looking at this part. Okay, this is as I said earlier, this is a basic block diagram of binary baseband transmission. So we have a transmitter, we have a receiver. In between, we have a channel. But in the transmitter, before you transmit, you have a transmit filter. And we go through the channel. And at the receiver, the first thing to do is receive filter. So after the receive filter, you are going on to the demodulation process. Okay? So right now, we are learning about how we design this red block, okay, this whole block. Okay, what is the ideal or theoretical block for this whole thing, and also how we can design and what is the example of this transmit filter and what is a receive filter. So that's what we are learning. Okay, channel we are not learning. Only thing we learned about the channel is that this channel probably is 8WGN noise. Okay, noise channel. Later, probably much later, some of you probably learned that the channel sometimes has a wireless fading channel, but that's a little bit complex issue. So we don't learn channel. But what we know is that this channel is a very bad guy. Okay? So we cannot control this channel. So only thing we can do is we design transmit filter and receive filter. So how to design the transmit filter and the receive filter is that when you put the transmit filter and receive filter and put them all together, we want to make this whole thing to work as a Nyquist channel, okay? Ideally speaking. So that's what we want. If you want to make this whole thing to be Nyquist channel, that basically means that input and output has no ISI, right? Output has no intersymbol interference, okay? Because in order to make no intersymbol interference at the output, that is why we want to make a Nyquist channel. Okay? That's ideally, theoretically, that's what we want to do. So to do that, for transmit filter, okay, what we learn is that we design this transmit filter using a raised cosine. Okay, we learned the raised cosine, right? That's this part, raised cosine. So main reason that we use this transmit filter and main reason we use a raised cosine is because that we want to shape the pulse. That's why we call that as a pulse shaping filter, right? Pulse shaping. So you want to shape the pulse, make it round a little bit. So that way eventually we want to make a spectrum. Eventually the goal is we want to reduce the out of band spectrum. Okay, so that's why we use this one, pulse shaping filter. We shape the pulse in order to make a good spectrum in frequency domain. So that's the reason we use this one. Receive filter, we're going to learn today. Okay, we're going to learn today. So that's basically the whole idea. So these equations you see here, all of these things are regarding the whole block as a Nyquist channel. So these all equations are regarding Nyquist channel. So eventually, Yi is the output of the whole red block here, right? That is Yi. Input is Ai, Ak. So that's the input. This is the input, Ak. Yi is the output of the red box. And PT is the red box as a whole, right? So this particular relationship, this is a convolution of input AK and the PT. PT is the red box, right? Red black box. So that is a convolution. That's going to be output Y. So since this is a summation, especially infinite summation, now you can rewrite this one into this way. What we want is, this one is the Y, this is output, but we are getting the ith sample. I maybe is 0, 1, okay? That's a sample number. So when you get the ith sample at the output, same here, right? This one and this one same. Ith output sample, is only a function of ith input sample and multiply with the constant. That means this is I, right? Input I, output I. These are the same input, same output. The input output at the same time, right? Ith input, ith output. This is actually same index. And what we want is we want to get only this one. This is only what we want, right? All the other terms contribute to make an intersymbol interference. So we want to remove all these things, right? Eventually, that's our goal. So once you do that, once you remove this ISI, intersymbol interference, eventually this is going to be input-output relationship. We have output. This is input. Root square E is simply constant. So this is simply a input and output. Input goes through the output with some constant. Okay? So this is what we want eventually. Once we have this relationship, what that means is this is AI. We have YI, and YI equals some constant times AI. So that's eventually the relationship we want to get. Okay? Here, this is complex, very complex. Right? Inside here, very complex. We have filters, we have a very complex channel. But anyway, if we design it very well and put them together, then we want to make a very simple input-output relationship. That's what we want. Simply, okay? That's what we want. And ideally speaking, how to design such things is based on this Nyquist channel. This is the ideal way of designing that red box. Ideal way. Now, so if we design Nyquist channel, then what that means is this Nyquist channel will have this time domain relationship, the frequency domain transfer function. Okay? So what you see here, time and frequency, is the time domain impulse response frequency domain transfer function of this block. We are looking at this block. So just looking this one as simply one block and call that as a PT in time domain, capital PF in frequency domain. So that's what we see here. Okay? So if we can make that red box to have this impulse response and this transfer function, that's perfect. That's a Nyquist channel, and that's what we want. And if we make it this way, then we are going to get this relationship, simple input-output relationship. Okay? So that's what we want eventually. But the problem is that look at this impulse response in time. We have some minus time thing, right? So we cannot implement this one this way. So this is only in theory. What we need to do is we have to implement a little bit different way. But this is a theoretical design of this PT. Okay? So this pulse shaping filter is regarding the transmit filter. So going back here, we are now talking about this one. Nyquist channel is about this whole thing. This whole thing, we want to make it as a Nyquist channel. Why? Because we want to make an output yi equals to c time. We want to make a simple input-output relationship. That's why we want to make this whole thing to be Nyquist channel. Okay? So Nyquist channel is about this whole thing. Pulse shaping filter is for this one. Okay? This is a pulse shaping filter, transient filter. Okay? So pulse shaping filter is here, and this is pulse shaping filter. And the most common example of pulse shaping filter is raised cosine pulse. Okay, so this raised cosine pulse spectrum, this raised cosine is an example of pulse shaping filter. Again, this is a transmit filter, right? So let's take a look at this raised cosine pulse. We can take a look at this one here. This is a frequency domain. Okay, and this is a time domain. So let's think about this way. Let me summarize the picture here. So we have an input, And as we said, we have a PT, we have YN. Let's call this PN. So we have this block, right? Maybe you can make it a little bit more clear. We have a transmit filter. Channel. Receive filter. This whole thing is a PT. Now we have output. Let's call this YM. Okay? So that's what we said, right? And as I said, this whole thing PT, we want to make it as a Nyquist channel. That's our goal. Right? We want to make this whole PT as a Nyquist channel. Okay? Why? Because if we make this blue one, this whole thing, okay, if we make this whole thing to Nyquist channel, then we know that the input-output relationship is going to be very simple as this way, right? So that's why we want to make whole thing to be Nyquist channel. Now let's look at the Nyquist channel. Nyquist channel has time domain relationship, time domain impulse response of sync channel. So let's go back to Nyquist channel picture. This is Nyquist channel, right? So Nyquist channel has time domain response like this and frequency domain response like this. That's the time domain and frequency domain response of Nyquist channel. Right? So if we make it perfect, like ideally, if we make this whole thing to Nyquist channel, then this blue diagram, blue box, will have a time domain response and this frequency domain response. That's our goal. Now, right now we are looking at only this part. This is called the pulse shaping filter. And example of pulse shaping is raised cosine. Now let's go to the picture of raised cosine. Raised cosine has this kind of spectrum or time domain response. So we have parameter called alpha. In pulse raised cosine, we have a parameter called alpha, right? So when you change the alpha to 0 or half or 1, now we have a different spectrum, different time domain response. So let's assume that alpha equal to 0. We pick the alpha equal to 0. In that case, what's going to happen is if we pick alpha equal to 0, when you design the raised cosine, we can pick a value. We can put the right value for alpha. And suppose that we pick alpha equal to 0. In that case, as you can see here, we can pick the alpha equal to 0. Also alpha equal to 0, right? In that case, time domain response, here, see, it is time domain. Time domain response is going to be sync function. This is going to be time domain. Let me see. We call this one as a GF. Yeah, so let's call this one as a GT. Okay, we are looking at this one. And the frequency response of this one, right, GF. Because when alpha equals to 0, this is going to be rectangular, right? So these things, I'm basically talking about the time domain response frequency transfer function of pulse shaping filter. I'm talking about pulse shaping filter right now, right? But I choose the alpha equal to 0. Now, what you can compare is that if when I design the pulse shaping filter, if I pick the alpha equal to 0, then this block, only this block, will give you sync function of time domain response and rectangular frequency response. But now going back here, eventually what we wanted was we want to design the whole thing to be Nyquist channel. Nyquist channel has a sync in time and rectangular in frequency. But this one, when you use alpha equal to 0, you already have that. So what that means is if alpha equal to 0, right, then this block actually has the exactly same response as Nyquist channel already. Okay? If the alpha equals 0, your response is already same as a Nyquist channel. Already, right? Only by one block, you already have that. In that case, yeah, so that's what it is. But alpha equals 0 actually is generally not possible in practical systems. So most likely, you're going to pick the alpha equal to some other value. Okay, alpha equal to 0 is not possible. Why is that? Because you cannot make a rectangular pulse in frequency domain in practical systems, right? So this is actually impossible. This is only in theory. So that's why, in general, let's say you're going to choose some other value. Let's say we pick a alpha equal to 1 over 2. In that case, when you pick the alpha equal to 1 over 2, what's happening is that in time domain, you're going to have not sinc function, but something like this. You have a little bit reduced pulse like this. And also in frequency domain, it's not rectangular. It's going to be like this. So that's what you're going to get for this transfer function, this transient filter. Okay? So this transient filter, by choosing alpha equal to 1 over 2, you're going to have this shape in time and frequency. Okay? And then you go through the channel. This channel always have inter-symbol interference here. Okay? So that's a scenario right now. Okay? So that's what we do here in raised cosine. Now let's think about this way. Let's just consider only, let's think about here. Okay, you have some raised cosine and you go through the channel, and what's the signal looks like here? Before the receive filter, what does the signal look like here? Signal here will look like this, because this is what you do, right? Okay, let me show you what it looks like. Right here, think about this way. Right here, we have simply pulse, like something like this, right? Maybe you have 1, 1, 0, 1, something like this, right? 1, 1, 0, 1, something like this, for example. Right? This is what you have here. I'm just giving an example. Okay? What's the signal looks like here? This kind of pulse go into the pulse shaping filter. So now you're going to shape it. Okay? So what does it look like? Right here. Right here, what's happening is every rectangle pulse will now, in time domain, every rectangular pulse you have, that is going to be changed. Every rectangular pulse you have, that's going to be changed as this kind of signal. That's what you have here, right? This is time domain, right? So originally you have a pulse, but when you go through the raised cosine pulse, now your pulse is going to look like a sinc function. Depending on what raised cosine pulse you use, maybe you can choose the alpha equal to 1 over 2. or maybe you can choose alpha equal to 1, right? So depending on the alpha value, exact shape now is different, but what's happening is originally you have a pulse coming in, and after the transfer filter, now your pulse now has a different shape like this. That's how we shape the filter, shape the pulse, right? This is original pulse, which is input. This is a pulse shaping filter, so we are shaping to make it this way. So now we have this input, right? Like a pulse, pulse after pulse, pulse after pulse. So now look at this way. We have a one pulse here, another pulse right after that, another pulse a little bit later. Then eventually right here, what it looks like is, for this particular pulse, the first pulse, it's going to be shaped and change it to this way, right? Like that. Second pulse, again, it's going to be shaped like that. This one also, right? It's just shaped like that. So that's what you're going to see. So eventually, when you add it all together, what you're going to see right here, okay, right here, what you're going to see is that something like that. You're going to see something like that. Okay? Some of these things you're going to see right here. Okay? So input to this transformer filter looks like this, simply a rectangular pulse. Every rectangular pulse now will be changed into this shape, right? Because that's why we use this. Every rectangular pulse, we shape it like this, shape it. But you have a multiple rectangular pulse, one after another. So every rectangular pulse will be shaped, every pulse, right? And you add it all together, that's gonna add it all together, this is what you're gonna get. So your signal right here will look like this. When you compare this original rectangular pulse and this one, when you compare these two, what's the difference? The difference is that this original pulse has this kind of frequency response. Because this is rectangular, right? Then frequency domain, it's going to be sync function. So you have a lot of energy in out of band. But when you shape it like this, right? And when you plot it in frequency domain, now your frequency domain will look like your frequency response, your spectrum will look like this. So you have a very, very little out of band spectrum. Because these out of band will be used for someone else, right? Some other people will use this band. This is not your band, right? So you should not have this much energy. In that case, you are interfering other users, right? So that's why we are shaping like this. Eventually, we want to change this kind of spectrum to this way. So we need to reduce that. We cannot make it zero, but we need to reduce it as much as we can. So this is frequency spectrum, again, frequency spectrum. This is time domain, this is frequency domain. After you do a shaping filter, this is time domain response, this is the frequency domain. And this is why we use shaping filter. Okay? Now the problem is that after that, this kind of signal, time domain signal now goes into the channel. This channel has a lot of inter-symbol interference. This one has a lot of multipath. So that is now the problem. So because of that, if you look at here, this point, after the channel, you transmit this signal over the air. Now that this signal goes into the channel, like this wireless channel, and right after that, if you look at it, now what is happening is that this signal something like that. So this one is a little bit delayed version. There's a little bit delay. There's again some delay. So these, remember that we discussed the memory in the channel, right? Remember the memory that I discussed? So memory will create intersymbol interference. If there's no memory, no ISI. Okay? When you go all the way back, when we discuss the intersymbol interference, this intersymbol interference happens because of this memory. Because of the memory, the previous signal remains inside the memory, and now it pops out a little bit later, after some delay, right? So this memory always creates ISI, intersymbol interference. So because of that memory in the channel, this can be wireless channel, any channel, but channel typically has a memory. So because of the memory, this signal goes into the memory, because this signal is now go into the channel, right? So channel inside has a memory, so this input goes into the memory and now comes at different time. Okay? This signal comes out at one time, and a little bit later again comes out, and a little bit much later it again comes out from another memory. There's a lot of memory inside. So that's why we have a multiple output at different time with a different delay. And eventually, what you're going to receive here, what you're going to see here is adding all together. So what are you going to get? If you add, I'm just giving an example of 3 taps. In fact, in the channel, there are much more. There are maybe 100 different outputs come together with a different delay. So when you add all together, it's going to be like something like this. You're going to get something like this, right? When you add all together, you're going to get this. So now the problem is, this is what you receive. From here, we have a receiver, right? Receiver. This is what you're going to receive from the receive antenna. Okay? That's what you're going to receive. We have done transient filter, so we do the pulse shaping like this. Okay? And also, we make a modulation, and we make some pulse or some digital data. And we cannot transmit the digital data as rectangular pulse because of the out-of-band spectrum. So that's why we put that into a pulse shaping filter in order to make a shape the pulse. That way we can reduce the energy at the out-of-band. Now transmit it, but channel is really a bad guy. So we have a lot of memory inside. Because of that, we have a lot of intersymbol interference. That way, what you receive, okay, in the receive antenna, what you receive looks like this. So now our goal is, when you receive this, we want to recover this. Because this is the original information, right? But this is what you receive. Now the question is, how can you recover, how can you go from this to this? How do you recover this? How? So that's the question. This is what you receive. We want to recover this originally. So that's the eventual goal. Okay? That's our goal. And what's happening is, if we design it very carefully, this block, receive filter, that's what we're going to do in order to recover from here to here. So this receive filter is going to receive this, okay, and do something and recover this block. So that's why we need this receive filter. Okay? So that's what we're going to talk about today. So that's the whole story. You don't have to remember the equation, okay? Just remember and understand this whole logic. So that's why we have these kind of raised cosine pulse, right? Remember this kind of pulse, and remember the reason why we are using this pulse, because of the spectrum, right? We want to remove the out of band, the spectrum. We learned the eye pattern, and what was the eye pattern? Eye pattern is measured here, right here. Okay? You measure the eye pattern right here. And why do you measure the eye pattern? We measure eye pattern because we want to learn, we want to understand the channel. Right? If the channel, let's say channel is perfect. Okay? Let's suppose the channel is perfect. If the channel is perfect, then this is what is transmitted, right? You go through the transmit filter, so this is what you transmit. And let's say channel is perfect. Then this is what you're going to receive here, right? So when you measure the eye diagram for this one, channel is perfect, so this is what you receive here. So when you measure the eye diagram will be very clean, like this, very clean. But in general, this is what you transmit, but you have a channel, but channel always have ISI, always timing, jitter, frequency, offset, there's many others. So because of that, you're not going to receive these things, right? You're going to receive something else. So that's why when you draw this eye diagram, overlap, put this again, and draw eye diagram, overlap, then you're going to see some very dirty picture. Okay? The eye is sometimes closed because of the noise and because of all the interference and all that. Eye is closed, right? And sometimes if the timing drifts, then this line, because you are drawing again and again, right? If the timing is drifting, then it moves here. When it moves, then everything is now, eventually everything is going to be black. Draw, right? Think about it. Everything is going to be black. That means you have some timing issue here, right? So this eye diagram is not to recover the data. This eye diagram is to analyze the system and analyze the channel. By looking at the eye pattern, eye diagram, now we understand that, oh, our channel is very bad one, and we have some timing issue. We have some frequency jitter. Okay? So we just find what is the channel looks like. That's the only thing we can see from the eye diagram. So eye diagram helps you. Okay? Gives us some information to you about the channel. So that's the only thing that's the only reason we use eye pattern. Now, important thing is this receive filter. So as I said, we receive this one. Okay, this is what we receive. From here, we need to recover this. So that's what we need. And that's why we need equalization or equalizer. So this receive filter, okay, this block, we call that as a transient filter, right? Transient filter is also called as a pulse shaping filter. And one of the example of pulse shaping was raised cosine. Now let's consider receive filter. Receive filter, in this particular case, we can call that as an equalizer. And there are many examples of equalizer. Many examples. Zero forcing, MMSE. There are many different filters, many different equalizers. So this one we call that as an equalizer. And that's what we are learning here. Okay, equalizer. Simply speaking, equalizer here is filter, because it says a receive filter, right? So equalizer is a filter, simply. Now let's think about Why we call that as equalizer? You know, some senior persons, right? Like your grandfather, or you know, some senior person has some problem in hearing. So they typically use a hearing aid. You know, hearing aid? Yeah. So there's a hearing aid. You put it inside, right? Just to help you to hear some, hear some music, or you know, voice or something like that. So when you measure the your frequency response of your ear, okay, senior persons have this kind of transfer function. So what that means is your grandfather can still hear most of the voice, but he has some problem of hearing only a specific frequency. Okay, he can still hear. So depending on the frequency, some frequency he can still hear, some other frequency he has some problem in hearing. So that's the issue. It's not like he hear nothing. It's not like that, right? He still hears something, but some of the frequency he has some problem. So depending on the frequency, now he has some different gain or different issue. So what the hearing aid helps him is that hearing aid will put some gain here, like an amplifier for this particular frequency. Once you do that, what happens is, for this particular frequency, he can hear anyway, so hearing aid do nothing. But for this particular frequency, he cannot hear much, so the hearing aid will amplify it. Okay, amplify it so that he can hear. Because without hearing aid, he cannot hear it. It hears very small sound, so the hearing aid will amplify it, putting amplifier for this particular frequency. That's what the hearing aid. So eventually, once you use the hearing aid, he can hear all the frequency with the sum of the equal gain. So these frequency he can hear anyway. For this particular frequency, since the hearing aid is amplifying, right? Because of this hearing aid, you can still hear with a pretty good gain, right? So that's what the hearing aid does. That's why we need a hearing aid. So this is a concept of equalizer. You see the equal here? So that is a concept of equalizer. In frequency domain, even here in wireless communication, when you look at here, right, and when you look at the spectrum, frequency spectrum, it's not like a equal. Some frequency has, when you look at the frequency transfer function, some of the transfer function has a good gain, some of them low, some of them high, some of them low. This is what's happening of the frequency transfer function when you look at here. So when you get this kind of signal, I'm drawing frequency domain, right? When you put this kind of frequency response and put that into the equalizer, and eventually the output we want to get as equal. We want to make it equal. So this is the input transfer function in frequency domain, and after the equalizer, we want to get this output equal for all of the frequency. So you see you hear the equalizer in the audio system, right? In the home audio, stereo system. So what is the equalizer in that audio system? In audio systems, maybe you can see that like you have some switch, a lot of bar switch. So this is like 1 kilohertz, 2 kilohertz, 5 kilohertz, 10 kilohertz. Something like that, right? That's equalizer. or little bit low as 500 hertz. So what you do is that if you want to hear a little bit low frequency sound, okay, then you can increase the gain, or you can decrease the gain. That way, you are reducing the gain of this particular spectrum, right? Particular frequency. So what that means is, each of these is a frequency, like a frequency domain. Like this is 500 here, 1 kilohertz here, 1 kilohertz, 2 kilohertz, 5 kilohertz, 10 kilohertz. So if you just listen the music, then maybe the music that you're listening may have a little bit high power in the 500 megahertz, 500 hertz, and a little bit low power in the 1 kilohertz, something like that. I mean, this shape depends on the music that you're listening. Maybe you are listening like some music with a very low bass sound. In that case, you have high energy here, right? Something like that. Depends on the music. But what you want to do is, if you want that, oh, I want to hear this particular frequency a little bit clear, then you can increase it. Then you are increasing this, right? That way, eventually, you can equalize. It's up to you, right? So that's what we do. That's why we are using equalization. So it's just the gain, try to increase or decrease the gain of each particular frequency. So that way, I mean, try to make it equal gain for every frequency. So that's an equalizer. So same here, basically same concept. We have here in communication, right here before the receiver, if you measure the frequency function, frequency transfer function, it's not equal. Okay, it's like this. And then put this one into the equalizer, and eventually at the output, we want to make it equal gain at the frequency domain. Why do you want to make it equal gain, by the way? Why do you want to equalize it? So input is eventually like this, but after the equalizer at the output, you want to equalize it. So why do you want to equalize it? What's wrong with this one? Here's the reason. Think about a equal frequency response. That's why we want to equalize, right? Let's equalize it, and let's see we get this constant frequency transfer function. What does that mean? This basically means impulse in time, right? Impulse in time. Think about the inverse, the Fourier transform. We get this basically means this in time domain. And this is what we want, right? Remember the Nyquist channel. The whole thing that we want to do is to make this impulse response, right? That's our goal, actually. We want to have this impulse response. By making this impulse response, just single tap, now we can see that there's no intersymbol interference, right? Once we make this way, that means we have input and output, very simple relationship, like a yn. Let's see, there's a c here, then yn output is c times an. In order to make this simple input-output relationship, now we need to have this impulse response. So that's what we need eventually. But in order to make this impulse response, now we need to equalize in frequency domain. So these are same thing, right? So that's the main reason, and that's why we need to equalize it. Okay. So that's a main idea, but putting another way, what that means is here, right here, right? As I said, here we have this kind of input signal, right? So input here is not equal. We have up and down in frequency domain. What does that mean? That basically means is when you look at here, in time domain, frequency domain is going up and down. But in time domain, what that means is we have multiple paths. Impulse response is not just one pulse, one impulse. We have a multiple path. Right? If we have only one path, one tap, then it's going to be equal, right? But here it's not equal. It's not equal. That's why we use equalizer, right? We want to make it equal, but before equalizer, it's not equal. Like up and down in frequency domain. That means in time domain, you have a multiple taps. So eventually, what equalizer does is, let me put it here. What equalizer does is that input to equalizer in frequency domain, it's like this. And in time domain, it's like this. That's input to equalizer. And after the equalizer, we want to make it this way. That's why we make it equal. That's why we call this equalizer, right? Equalizer. And in time domain, we want to make it this. That's why we need the equalizer. Okay? That's the main goal of equalizer. Make it this kind of input signal to this output. So once you have a perfect this input output this time and frequency response, okay, if we get these output here, that means now we perfectly made this Nyquist channel, because that is Nyquist channel we wanted, right? That is Nyquist channel. So that's what we get. So that is equalization. Okay, that's the basic idea of equalizer. Does it make sense? Yeah, it's a basic idea of equalizer. But now, to be more detailed, now we need to discuss how to design this equalizer. So how to design equalizer actually is very complex. To be honest, there are a lot of different equalizer design. And if we want to cover that, that's going to be probably one semester of work. It's a lot of work. But what I'm trying to introduce you is probably the basic ones. So how to design it here is that equalizer is, again, just a filter. Okay, simply a filter. So let's see. I'll give you one example. Okay? So let's say I'm going to make this whole block diagram to very simple. This way, okay? So right here is here. And we have equalizer or receive filter, same thing, and we have output here, okay? So because we want to focus on only equalizer, so let's make a simple input-output relationship at the equalizer, okay? Just make a simple block diagram. Now what I like to do is I like to call this input to the equalizer to be CT or CN. Okay, and equalizer has a multiple taps because this is a filter. And when you draw the model for the filter, typically we draw this kind of way. This is called the tap delay line model. You see here delay line, right? So each one is called a tap. So that's why we call this kind of model as a tap delay line. Tap delay line model. This is a most common model for filter. Okay? Every filter typically is modeled by tap delay line model. What that means is this equalizer filter, I'm going to use it like this way. So we've seen this kind of picture many times, right? I used this model many times earlier. So this is tap delay line. We have 3 taps. Each one is a tap. And each one is a delay, right? And inside here, you see that there is a line connected to each tap. So that's why we call that as a tap delay line. This is the simplest model that we can represent filters. Equalizer is again just one of the filters, so we can use the same model. So let's use this model, and in this particular example, you assume that there are 2n plus 1 taps. First thing to decide is you need to decide how many taps you're going to have. Okay? You need to decide how many taps. But just for example, let me assume that my equalizer has only 3 taps, like this. Okay, and now I'm going to put the middle one 0, and here minus 1 and 1 for delay. Okay. And I'm going to call the weight or the gain or coefficient for each one as this way. Okay, so Wn is my equalizer coefficient, Wn. So what that means is each W is complex value, A plus JB. Okay, so each one is a simple value. So we have 3 different values. This is how to calculate the filter generally. And after that, now we have our output Y. So let's call this output as Yn. So Cn is the input to the equalizer. Now equalizer looks like this. We have multiple taps. So how many tabs we have, we need to decide. So in order to just simply show you, I just picked 3 tabs. Simply 3 tabs. And each tab has some coefficient. Each one, W minus 1, W0, W1, each of them is a different value. And this one, each one is a complex value. A plus JB, C plus JD, something like that, right? So that's what we need to, that's what we have. And in order to design this equalizer, you need to decide the 2 things. 3 actually, 3 things. 1, how many tabs you need to have. That's the first thing you need to decide. Second thing is, what's going to be the delay value for each one. And the third thing, most important thing is, you need to decide W values. Each W is complex value, so you need to calculate them. So once you decide these 3 values, how many taps, and what's going to be the delay, and what's going to be the W value, you decide those 3 values, now you designed already the equalizer. Okay? And I'm going to show you, how to do that. So let's say we have these things. For this one, as an example, I decide that the number of taps is only 3, and the delay is simply minus 101. Okay? I have decided 2 things. 3 taps and delay is minus 101 as an example. Okay? But I don't know is the W1, this W value I don't know yet. So I need to decide what is going to be the W value. So how to do that is, when you look at the input-output relationship, we know that this output Yn is simply convolution of input and inverse input and the Wn, impulse response, right? This is going to be input relationship. And this convolution is a summation, right? So therefore, what that means is, this is going to be like that. We're going to have something like that, right? That's going to be our input-output relationship. Just a simple convolution. Convolution, right? Simple convolution. So what that means is, That's what you get. Because I have only 3 tabs, we're going to have only 3 terms in the summation. So that's the relationship between the output and input and equalizer. So that's the relationship, right? What I have here is simply a convolution between the input and impulse response of the equalizer. That's going to be output, right? That's simple as that. Let's look at the example here. Since n can be anything, n is a sample number, so let's see that y0 is, you can put the n equal to 0 here. Then w minus 1 c1 plus w0 c0 plus w1 c minus 1. y1 is w minus 1 c2 plus something like that, right? Something like that. So this is simple example, but when you put that in equation, this is the equation. And when you look at here, right, these equations, what we can see is that it's going to be much easier if you write all these things in matrix. So these things, now we know that it's much easier to write it as a matrix. Okay, so let's write it as a matrix. That's the matrix notation. So this one is simply an addition of these 3 parameters, right? And we can see that this one, you have a W1, W minus 1. Here again, W minus 1. We have a W0, W0, W1, W1. So you can separate C matrix with the W matrix, right? When you do that, you're going to get Y vector, right? So simply a matrix notation. The same, basically, right? So C1 times W minus 1, C0 times W0, C minus 1 times W1. That's the same as this one, right? You can write it as a simply matrix. But what we can notice is that eventually what we want, let's look at here. Y0, that's the output of the equalizer here, right? What we want is output of the equalizer is only a function of input at the same sample index. That's eventually what we wanted, right? We remember what we always want is this one. This is what we want all the time. Here, what we wanted is y0 is a function of input c0. So that's what we want. y1 is only a function of C1. That's what we want. Okay? So what that means is we want to remove this. Remove this. Because those are intersymbol interference. Okay? That's what we want. That's what we want. So therefore, what we want to do is that when you multiply these 2 matrices, right? These matrices, eventually we want to make these matrices to be something like this, or some constant value. Eventually, this is what we wanted. When you multiply these two matrices, we want to get this output. When you multiply these two, and then you get this output, that means this term will be 0. This term will be 0. You only have this term multiplied by some energy. Same thing for the next one. You remove this one because it's a 0. This one 0. Only the middle one you want to multiply this energy, and that's only what you want. So when you multiply these two matrices, you want to get this output. That's the goal of equalization. We're talking about this one, right? That's what we want. So this is going to be the relationship of the equalization. And in here, we already know the C, because C is the input. And what we don't know is W. We don't know the W. That's what we want to get, right? So simply, when I write this matrix equation, I can write it as this whole matrix as a C. This whole matrix is W. So C matrix times W equals to 0 root square E 0. This is the relationship. And what we want to know is W matrix. C matrix we already know. And this output, of course, we know. So how do you get W? W is C inverse this one. Right? C is a square matrix, or you can make it square. So you can take an inverse matrix and then multiply with this. That's how you calculate the W. And once you calculate the W, like this way, now then you calculate all this value all together. That's going to be your equalizer. So that's what you see here in this equation. So this equation you see here is the case of a 2n+1 tap. What I show you here is only 3 taps, right? But this is a general way. 2n+1 number of taps. So we have a more number of taps, but the same idea. That's why we have this equation. So this is how to calculate all this W matrix, the equalizer coefficients. Okay? Yeah, so that's the idea of equalization. Okay, so let's continue next time.